Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
Today I'd like to talk about our universe, which is a pretty big topic. I like to focus on the formation of structure of the universe. So on the left, you can see this picture. This is a very early picture of our universe. So this is basically a two-dimensional observation of the very early universe and projected onto an oval that looks like this. So you sometimes see that the world map is projected onto an oval, so this kind of projection. And this is a very early picture of the universe. On the right-hand side, you can see that this is the universe today, or the galaxies we observe today. So today I'm going to talk about how the universe starts from very early on, very beginning, small perturbation, and grow into all the galaxies, all the spectacular galaxies we see today. And for me, this just is like a sophisticated and beautiful orchestral music. So I named my talk Rhapsody, and also a name of the simulation, which I'm going to show you. By the way, I love the acoustic in here auditorium. I can wait for that. The study of our universe is called cosmology. According to the New Oxford American Dictionary, cosmology is the science of the origin and the development of the universe. Today, I'd like to focus on this development part of cosmology. And the dictionary also says that modern astronomy is dominated by the Big Bang theory, which brings together observational astronomy and particle physics. I'd like to emphasize this word observational. What I'm going to talk about today is heavily rely on observational evidence, and which can help us to test our physical models. So two of the very important assumptions in cosmology. The first one is this Copernican principle. Copernican principle is basically named after Copernicus, who said that the Earth is not the center of the universe, and which basically says that there's nothing special about our location in the universe. The physical laws that applies on our Earth also applies to the space. That's the basic assumption in cosmology. And another important assumption is that the universe is homogeneous and isotropic on large scales. So you can see that we are talking about sufficiently large scales so that things start to look homogeneous and isotropic. This is our address in the universe. So we are here on the Earth, which is 8 light minutes away from the sun. And sun is just one small star in this Milky Way galaxy. And in Milky Way galaxy, there are 100 billion stars, just like our sun. And our galaxy is just one small point in this local group. Each point is one galaxy. And this local supercluster spans a couple million light years. And this local supercluster is just another small patch inside this large-scale structure. So today I'm going to talk about scales beyond several million light years above galaxies. So I have just said several astronomical numbers. And I'd like to demonstrate what an astronomical number is. Here is a box of glass beads. So you can see that these are glass beads. And each of these particles is about 1/100th of an inch. So how many particles do you think is in here? Million, billion, trillion?
Million.
So the correct answer is actually about 100 million. So I said that there's 100 billion stars in our galaxy, which means that I need 1,000 of these boxes, and each particle will represent one star. That's how many stars there are in our galaxy. So this is the distance dimension of our universe. And there's also this time dimension of our universe. In astronomy, when we look further, we are actually looking back in history, in the history of the universe. So every generation built better and more powerful telescope to look further back and basically look further back in the history of the universe. Astronomer Edwin Hubble once said that the history of astronomy is the history of receding horizons. And we are arguably in a very exciting era that we can start to see very early on in the universe that start to answer many questions about our universe. So we now think that the universe starts with this Big Bang, or basically the starting point of the expansion. And the universe was small and hot and dense early on, and then it keeps expanding. And then there's, at some point, it emits this cosmic microwave background, which I will explain. And then stars form, galaxies form, and they evolve. And later on, dark energy takes over and causes the acceleration of the expansion. So the story I'm going to tell you today is that how does the structure in the universe start from very small perturbation very early on? And the small perturbation is told us by this microwave background. And how does these small perturbations grow into structures, cosmic structures? And later on, how does the growth of structures slow down by this dark energy? So I just said that the universe is expanding. So early last century, people start to realize that our Milky Way galaxy is not the entire universe. There are galaxies outside our Milky Way. And about exactly 100 years ago, Vesto Sliver discovered that redshift of galaxies, meaning that he found that most galaxies are actually moving away from us. And a little bit later, Edwin Hubble found that, or he measured the distances of these galaxies. And he found that the velocity of galaxies and their distances lies on a straight line. Or velocity and the distance are proportional to each other. And he found that this is a characteristic of an uniformly expanding body. And actually, Hubble's law was not first derived by Hubble. It's actually first derived by Georges Lemaitre, a Belgian physicist. This Hubble's law is actually a very generic property of an expanding body. Now I'd like to demonstrate this expansion. It's hard to do it in 3 dimensions, so we start with 1 dimension here first. So each tape here represents a galaxy. And the universe is expanding, so you can see that these galaxies are moving away from each other. And let me try it again. So if you focus on like these 2 galaxies, and the farther it's away from me, and it's actually moving faster away from me. And that's the characteristic of an uniform expansion. And next, I'd like to demonstrate that in a 2-dimensional sphere. In a 2-dimensional sphere, actually there's no so-called center, so you can just focus on one random point, and every point will behave the same. You can see that there are some stars on this balloon. Unfortunately, we couldn't find one that with galaxies on the balloon, so we'll just pretend that these stars are galaxies. By the way, I like to emphasize that the universe is expanding, but our galaxy is not expanding. Our solar system is not expanding. We are not expanding. And because the galaxy is bound by gravity. And so the distance between stars are not expanding. So we have to pretend these are galaxies. So you can see that the distance between these galaxies are increasing. And just like in the one-dimensional case, that further away the galaxies are apart, and the bigger and the faster away they are moving from each other. So I guess I need to explain. I need to prevent it from popping. So let's take a look at this equation. V equals velocity equals Hubble's constant times distance. So if the distance is very large, and this v can be greater than the speed of light. But we know that Einstein told us that nothing can move faster than the speed of light. And what's wrong with this? So it's actually not the object that's moving. That is, the space in between objects are increasing. So this is like a physics in an evolving background. For example, if I'm doing experiment on a desk that is shaking or wobbling, and then all the physical laws I derive from this experiment will be wrong because the table itself is shaking. So if I take out the effects of an evolving background, then physical laws will still work. So in an expanding universe, we need to take out the expansion so that the physical laws still work. The expansion of the universe has a very important consequence called redshift. So here, let's look at, again, an expanding balloon analogy. So now we put grid on the balloon, and there's some wavelength. And as the balloon expands, you can see that the wavelength are stretched. And longer wavelength means that the light is redder, or close to red. So, which means that an expanding universe will make the wavelength stretched and become redshifted. So when we say a galaxy is at redshift 1, what do we mean? Or a galaxy has redshift 1, what do we mean? So we look at the spectra. Spectra is these figures on the right-hand side. And in the lab, we have the unshifted spectra. And we observe the spectra of galaxies, and we compare these spectral lines. And we can find how much the spectral lines are redshifted. For example, if the galaxy, its wavelength is stretched by a factor of 2, means that when the galaxy emits its light, the universe was half the size today. And between the time that the galaxy emits its light and the time we receive its light, the universe has expanded by a factor of 2, and we call that galaxy at redshift 1. So in this talk, therefore redshift and distance and cosmic time can represent each other. And in this talk, I'll use them interchangeably. So the universe is expanding, which means that it is smaller. And if it's smaller, then it has higher density. It means it's hotter in the past. So there's this Big Bang theory that indicates that the universe starts very small and very hot. And people start to look for the echoes of Big Bang. So the Big Bang, in this very early universe, very hot and very small, dense region, so it must have some remnant heat that can be detected to us. That's predicted by the Big Bang theory. And it was actually accidentally discovered by Arnold Penzias and Robert Wilson in 1965. So in this picture, you can see the antenna that Penzias and Wilson used to found the microwave background. So Penzias and Wilson were radio astronomers in Bell Labs in New Jersey. And then they used this super sensitive antenna to look at the sky. And they found there's this uniform noise that comes from all directions of the sky. And they were pretty puzzled. And they were extraordinary radio astronomers. They very carefully calibrate out all the noises, including the radio interference from New York City and the interference from our own galaxy, and also stars. And they also go take a look at the antenna, and they found the antenna was full of bird droppings. And then they took time to clean up all the bird droppings and chase out all the birds, but they still saw those uniform signals. And they talked to their friend, their physicist friend, and turns out that several cosmologists in Princeton University, that's not very far away from Bell Lab, heard about this, and they immediately realized that they found the echo of the Big Bang. And it's a uniform noise from all directions of the sky. It's the same day and night. So it couldn't be anything inside our solar system or related to any special objects in the sky. It must have come from the universe. And Penzias and Wilson won the Nobel Prize in 1978. Just to say a few more words about the Big Bang. So the CMB is a uniform black body radiation. So in the 90s, the COBE satellites measure the energy spectrum of CMB, basically this intensity as a function of frequency. And then they found this characteristic shape of a black body radiation. What does it mean that the universe was a black body radiation? Remember, these lights are from very early universe. Back then, the universe was very hot, very dense. It's basically in thermal equilibrium. And this black body radiation is a characteristic of this early thermal equilibrium. And in this early universe, it's basically everything was ionized. There were no atoms. There were only protons, electrons, and photons. So photons and electrons are in equilibrium basically means that photons are constantly bouncing back and forth between electrons, or we call them scattering. So photons cannot travel as a straight line. So back then, the universe was basically opaque. It's just like you are in a very thick fog. So photons are bouncing back by these water molecules so that the fog appears to be opaque. And then when the universe cools down, and then it starts to become transparent. So the electrons are bonded to protons to form atoms, and then now the photons can travel freely to us. And that's when we can start observe the CMB, which is 380,000 years after the Big Bang. So I just said that the CMB is a very uniform background, but there is actually tiny, tiny fluctuations, 1 part in 100,000. And this is the measurement by WMAP satellite. And this 1 part in 1,000 fluctuations, we can see that these hot and cold spots basically means the temperature perturbation in this sky. And also which correspond to the density perturbation in the very early universe. And these tiny perturbations will later grow into the structure we see. And again, this is how it looks like on a 2D sphere. And you can see that there's this red band in between. These are our Milky Way galaxy, which also emit microwave. And in this map, this one has been calibrated out or taken out. And again, it's a 2D sphere and projected onto an oval. And I'd like to talk a little bit about this WMAP, or Wilkinson microwave anisotropy probe, which made the beautiful map we just saw. And this WMAP is named after David Wilkinson, who was actually born in Hillside, Michigan. So if this is the Michigan pond, and Hillside is around here. And he went to undergrad and also graduate school, both in the University of Michigan, and even taught a couple years here. And then he went on to become a professor in Princeton University. And he was one of the pioneers in these CMB experiments and observational cosmology experiments. The plot in the black body radiation plot I showed you, he was one of the contributors. And I also like to talk about this instrument, WMAP. So you can see that sun was further away and the Earth is a bit closer. So you can see that it's basically in the shadow of the Earth, or the other side of the Earth, opposite to the sun. So this is a location where we call L2 point. It's one of the Lagrange points. So at this location, the gravitational pull from the sun and the Earth provide the centripetal force to support the rotation of the satellite. So the satellite basically have the same period as our Earth. It's basically just always in the shadow of the Earth. And it's 4 times the Earth-Moon distance. And it was launched in 2001 and retired in 2010. And it was actually boosted to a slightly larger distances. There was this place called graveyards for retired satellites. And they're just basically orbiting there, become one of the space junk. I was actually pretty shocked to hear that WMAP will one day retire, because I thought WMAP should just, like Hubble Space Telescope, will work forever. But apparently it didn't decommission 2 years ago. And the next generation of the satellite, the microwave probe, is this Planck satellite. Of course, it's named after the German physicist Max Planck, who first derived this black body radiation. So you can see that it's launched by this European Space Agency 3 years ago. And you can see that it's rotating. Oh, by the way, it's also in the same location, the L2 point, the same location as WMAP. You can see when it's orbiting, it's scanning the universe in this configuration. So it seems like it's shooting light. Actually, it's not shooting light. It's receiving light from the early universe. And it has much better resolution than WMAP. And one of the important missions of Planck is to measure the polarization of this CMB, basically to see if there's any preferred direction of the electric field of these radiations, of the oldest light in the universe. And this polarization information actually carries about the information about the very early universe, the gravitational waves, and inflation. Inflation is what seeds the fluctuations here, but I'm not going to talk about inflation. And in the very last, you can see that how does this 2D sphere unfold or projected onto this oval shape. I've talked about the early perturbation that's revealed us by this cosmic microwave background. Now I'd like to talk about how do these small perturbations grow into the large-scale structure. And before I tell this, I need to talk about dark matter, because dark matter is very important in the formation of structure. So dark matter basically is some matter in the universe that do not have electromagnetic interactions. Therefore, it doesn't emit light, does not absorb light. And the dark matter was actually first derived from looking at the dynamics, or basically the motions of galaxies and stars. So we know that in a gravitational system, the gravitational potential and kinetic energy should be comparable. And when they observe galaxies or stars in galaxies, they found out their kinetic energy is much bigger than the gravitational energy. So there must be something wrong with the gravitational energy. So they need to so there must be some invisible matter exist to provide this gravitational energy, so that to support the motion of galaxies and clusters. And here is a picture of a galaxy in between. And this is an artist's illustration of the distribution of dark matter around the galaxy. So you can see that these are the dark matter halos, or basically a very high density region of dark matter inside which galaxies form, and dark matter halos will support the rotation of these stars. Astronomers have been using gravitational lensing to map out the mass distribution. So this is the mass distribution of dark matter. So you can see that galaxies more or less trace the position of this dark matter halo. And it turns out that galaxy cluster has a third component, that is the hot gas, which emits X-ray. So as I said, that galaxy clusters are very big or massive system. It has a lot of gravitational potential. So when there is gravitational instability, and then the gravitational potential will convert into kinetic energy, and then convert to heat up this gas, so that galaxy clusters are shining in X-ray. So you can see that in X-ray, there's this beautiful ball shock, just like a bullet passing through the earth, passing through air. And if its speed is greater than the sound speed, and then you form this shock wave. And if we put all of them together, we can see that the dark matter and the X-ray gas are well separated. So this is a strong evidence that there needs to be two different components, gas and dark matter, that behave differently. And this is a very strong evidence of the existence of dark matter. And I just talked about galaxies and galaxy clusters. And galaxies and galaxy clusters are the building blocks of the universe. And here is the large-scale structure observed today, the same figure in the title slide I showed. And each plot, or each point here is one galaxy. You can see that this distribution is far from random. They cluster together to form galaxy clusters, and there seems to be some like filament structures. And there are places that there's nothing there, it's just like a void. And by the way, this is also the galactic plane, or our Milky Way, which blocks our view of other galaxies, so we subtract this out. So the big question is, how did the universe evolve from 380,000 years ago, one part in 100,000 perturbation, to the galaxies today? And the question is, how did the tiny fluctuation grow into large-scale structure? So we use computer simulations to understand this. Here is one example of the computer simulation. So in computer simulation, we set up the universe inside a box, and then we put in particles in it. And each particle represents some amount of mass in our universe. Or you can consider that these particles represent the density field in our universe. And they simulate the gravitational interactions between the mass inside the universe. And we call this n-body simulation. And in this simulation, I'm going to show that it includes 10 billion particles. This is the Millennium simulation done by the Virgo Consortium in Europe. And this is the simulation of the universe 200 million years ago after the Big Bang, you can see that there's very small fluctuations. And those fluctuations are consistent with the CMB fluctuations. And then you turn on gravity, and of course put in the expansion of the universe. And this structure grows into this higher contrast today. So let me flip through the evolution. So this is near the initial point. You can see the perturbations are pretty small. And there are some pretty big perturbations, for example, this point here. And then later on, you can see that the perturbation is amplified. And you can see that, and also the high density region becomes higher density, and low density region becomes even lower density. And it's further amplified. And this is the final picture of the simulation. You can see that now the universe looks like a web. You can see that all these filaments and joining these high density regions. And if we zoom in this cosmic web, here are these knots. These are the high density regions where galaxies and galaxy clusters will form. And they're joined by these filaments. And if we zoom in, this is a couple million light years. And by the way, it's MPC is megaparsec. 1 parsec is 3 light years. So it's basically similar unit. So you can see this is where a galaxy cluster will form. You can see that it has a very complicated structure. It has some neighbors, some galaxies, smaller, and sometimes it looks a little bit disturbed and has lots of structures. And there are these filaments that materials will fall in along these materials to increase the mass of this system. So next, I'm going to show you a movie which is part of my PhD thesis, which is an evolution of a galaxy cluster. And its mass is 10 to the 15 times solar mass. And it starts from very tiny little perturbation. And you can see that under gravitational interaction, that 3 clumps has already formed. And this one has kind of like a filament. And you can see that these two, because of gravity, they are interacting or closely merging with each other. And when they are merging, they are basically rotating around and transferring materials. And each blob or small point here you see is a high density region where a galaxy will form. And so this system will include about several hundred to 1,000 galaxies. So we can actually see the power of gravitational instability on our desktop. So here I'm going to show how small perturbations, you can see that a small perturbations on this soda can is amplified by gravity so that the whole thing collapses. And now I'd like to do another small demonstration showing the relation between dark matter and galaxies. So here is a piece of cloth, black cloth, which represents dark matter. And we put some fluorescent particles on it, which will present the distribution of galaxy. And originally it looks smooth, but I like to use my hand to simulate gravitational instability. And I just do some very nonlinear processes and try to create as much perturbation as possible on this sheet. And so I generate some creases on this dark matter density field. You can see that maybe here as well. You can see that these bright points or galaxies basically cluster or are concentrated on the region where there are big perturbations in dark matter field. And basically saying that the galaxies are tracing dark matter density fields, and they will actually be very clustered where the dark matter potential where there's very high density of dark matter. So these are, as I said, that galaxies and galaxy clusters are the building blocks of our universe. And they are basically the workhorse of cosmology because they are what we can observe and to trace dark matter. And it turns out that you can also contribute to the study of galaxies. And I'd like to introduce this very fun citizen science project called Galaxy Zoo. So this is basically asking you to classify galaxies. So this project includes many images from this Sloan Digital Sky Survey and Hubble Space Telescope. So these surveys basically scan the entire sky and found galaxies. And then they process these galaxies using machines or computer codes. But it turns out that human eyes and brain are much better at recognizing patterns than machine. If you ever use the digital photo album face recognition, you'll know that computers do not do very well in recognizing patterns. And also, the machine can only identify what it's told to be, the machine can only identify what we tell it to do. So it cannot identify new things. So this actually needs to be done with human eyes. Now I'd like to ask for a volunteer who thinks galaxies are cool. So here is one of the Galaxy Zoo example, and asking you to decide whether
if it's one of these?
Yes, exactly.
Okay. Smooth? This?
Yeah, but just
No?
Yeah, but I would say that this looks like this, isn't it?
I need my glasses checked.
You can
Okay.
click on it. So this one actually looks like, oops. Does this look like a desk? Build age on?
Could this be a disc?
Probably, yeah.
Yes. Yes.
Do you think it has a bulge at its center? Does this look at three of these?
Yes.
Okay, great.
This.
Yeah, and you have to make decision because anything odd? Well, there's something odd, I guess. There, could it be a supernova or another galaxy? We don't know. Maybe you could, yes?
Oh, and then what are the odd features? Other?
Yeah, maybe. And then we are done with one galaxy.
Yes.
I guess you have to log in.
Okay.
Okay, congratulations. You have made another contribution to our Galaxy Zoo. Thank you. So it turns out, what's your name?
Sue.
It turns out that citizen scientists like Sue have made lots of contributions to science. For example, this is called Henny's Voorwerp. Voorwerp means object in Dutch. So Henny van Arkel is a school teacher in Netherlands, and she participates in this Galaxy Zoo project. And one day that this object pops up on her screen. And what is this? And she emailed the Galaxy Zoo astronomers, also discussed this object in the forum. And this turns out to be a very interesting object. And many scientific paper has been written about it. So one of the theory is that this galaxy had an active nuclei, and then it brightened up this object. And so it turns green, means that it has some oxygen emission lines. And this active nuclei later shut off, but we can still see the echoes of that active nuclei. And another contribution from citizen scientists is this class of galaxy called green pea galaxies. And they are basically just like very green and compact object in Galaxy Zoo. So previously, nobody expected this kind of system to exist. But just thank our citizen scientists that it was found and classified as a new class of galaxies. And this green thing is actually very high star formation rate. And just not to be too selfish, if you have other passion, for example, stars or planets, which can be very interesting. And there are actually several sister sites, and they were all included in this zooniverse.org, whether you can do other projects, like participate in other projects. And there are even biology projects, oceanography projects, even humanity projects. And one day I find myself clicking about the classifying sea stars for the oceanography project. It's a lot of fun. So I've talked about the galaxy, the formation of structures. So do the structure formation go on forever? And do we get more and more galaxies? Will the universe become more and more crowded? And we now know that the answer is no, because of this dark energy. What dark energy do is to accelerate the expansion of the universe, but it also slows down the growth rate of structure. So let me first talk a little bit about dark energy. So I said that there's a lot of dark matter in our universe, and dark matter has gravity. Gravity is pulling things together. So previously, people thought that the expansion of our universe might be slowing down. And these scientists, Saul Perlmutter, Brian Schmidt, and Adam Rees, set out to measure what we call the expansion history of the universe, or basically whether the expansion is getting faster or getting slower. And surprisingly, they found that the expansion is getting faster and faster. Basically, the expansion is speeding up. And this is the tool they use, this so-called type 1a supernova. And you can see in this right-hand side, this picture, this is a white dwarf accreting material. And when the white dwarf reaches 1.4 solar mass, it will explode. And then because we know the physics of its explosion, we can compute its luminosity. And if we know its luminosity and the apparent brightness, then we can compute the distance. That's how they use it to compute distance. And distance of galaxies. You can see that here is a galaxy, and here's one example of supernova. You can see that the supernova is almost as bright as the entire galaxy. And then it just goes off, and several days later it dies down. And so this turns out to be a very powerful tool to measure distance. So to measure the expansion history, we basically need very accurate measurement of distances. So, and these scientists found that the universe is expanding and was awarded the Nobel Prize last year. So now we think that the acceleration of the universe is due to this dark energy. And dark energy was actually coined, this term was coined by Michael Turner at the University of Chicago. And he was also one of in the conversation with composer Philip Glass on the Einstein on the beach early in January. So here is one of the strong evidence that, as I said, that they measure the distance of supernova versus the redshift of these galaxies. And here are several models of the expansion history. And the data turns out to agree with this one, that the universe decelerates in the past due to the gravity of dark matter, and then actually accelerates now. But we actually don't know much about dark energy. We just know that it's smooth. It has a negative pressure, so that it's accelerating the expansion. And it's actually dominating the energy budget of the universe. I have been talking about dark matter and dark energy. What's the difference between them? Dark matter is attractive. So they basically are influenced by gravitational interactions. And dark energy, on the other hand, is repulsive and causes the acceleration of the universe. And as I showed you, that dark matter is clumpy. They have high-density regions and low-density regions. to provide the potential for galaxy formation. And dark energy, so far all the evidence, observational evidence suggests that it's smooth. And dark matter is some particles that's yet to be detected. It could be supersymmetric particles that might be detected in CERN or using gamma ray telescopes to observe, but it's still yet to be detected. And dark energy turns out to be a vacuum energy yet to be explained. It's actually much higher than the vacuum energy expected in quantum mechanics, which is a big puzzle at the moment of. And dark matter is 22% of the energy of total energy in the universe today, and dark energy is 37. So 73%. And just to repeat what I said, that dark energy dominates the early universe, and dark energy dominates the late-time universe. This is what I just said, that dark matter today is 23%, and dark energy is 72%. But early on, in early stage in the universe, it's actually dark matter was dominating. Dark matters are basically particles, so they dilute as the distance cube. But dark energy actually does not dilute. So early on, dark energy has very, very low density. But because it doesn't dilute, so then it dominates the energy density today. And this is, remember, this is when the CMB was emitted. And back then, dark matter dominates the universe. That's how the structure can form in the early universe. And here's my favorite episode from the piled higher and deeper PhD comics. So if you have no clue about something, astronomers answer, we put dark in front of it. It's easier to get funding. So since it's called dark energy, it turns out that the Department of Energy, who is interested in fundamental physics research, is also funding dark energy research projects. So how does dark energy affect the formation of structures? So here are two simulations, two numerical simulations. And this is a simulated universe with dark energy. And this is one with no dark energy. You can see that there are much more high-density regions if the universe has no dark energy. And this one is more like the universe today. It has like fewer bright regions or fewer structures. So this is a computer simulation, which we know that how much dark energy is in it. So in observation, if we go out, count how many galaxies and galaxy clusters in the universe are there, and then we can decide which one is closer to our true universe. That's how we use simulations to understand the properties. That's how we use simulations to help observations to understand the property of dark energy. So just as like what I just said, that we can just basically count how many galaxy clusters are out there and to determine the property of dark energy. Number of clusters as a function of cluster mass. So the one with dark energy will have fewer clusters. And this is one example of the experiments using clusters observed with X-rays. And these are two different redshifts. And these are data points, and the models agrees well with the one with dark energy. And I like to emphasize that this kind of experiment is actually not very easy. Let me use an analogy. For example, if I am assigned a task to estimate the weight distribution of the population in Ann Arbor, what am I going to do? I think that I have a room of audience, so I can ask for their weight, and so that I can plot a histogram of people's weight, so that I have an estimate of people's weight, of the weight of the population in Ann Arbor. But now I immediately have two problems. First, the audience in this room may not be representative of the population of Ann Arbor. First, you guys are people who are interested in physics, which may not be representative of the entire population in Ann Arbor. And second, you guys didn't sleep in on Saturday morning, which may not be representative of population of Ann Arbor as well. So we have selection bias, which means that our sample is not representative of the entire population. And the second difficulty is that if I ask you your weight, you might not telling me the truth. And it's either that you don't know how much exactly you weigh, or for any reason you just don't want to tell me the truth. So now we have measurement bias, means that we cannot get a precise measurement. So this actually happens exactly to this kind of experiment. So we observe galaxy clusters, but we don't know if we get a representative sample. And we don't know if we get the mass of galaxy clusters correctly. So what astronomers can do is to stare at galaxies and guess their masses. So galaxy clusters can be observed in several different ways. For example, in optical, like a Hubble Space Telescope image, so you can see that there are galaxies in it. So we can estimate that if there are more galaxies inside this system will be more massive. And we can also look at in X-ray, and it's brighter in X-ray, we think it will be more massive. And also, we can also measure it in microwave background. So it turns out that if we can measure the mass of the cluster more precisely, and we can get more information about dark energy. And part of my PhD thesis is try to use computer simulations to simulate the formation history of galaxy clusters. And because in simulations, we know the exact weight. And then we try to look at them as observers do. And then we try to understand how is the formation history impacts the mass. It's just like if I look at a person and I want to guess his or her weight, and if I get more information about his or her age or height or other lifestyle habits, maybe I can get a better estimate of the weight. So here I'd like to show you once again two movies. These two movies are the formation history of two objects, and they have the same mass today. And you can see that they form actually quite differently. So this one forms along a big filament. You can see that, and it basically has a very sociable life, has a lot of neighbors, lots of stuff falling in onto it. And this one has much fewer structures around it and has a quieter life. But it turns out both of them have the same mass. That's why the mass estimate of these systems are difficult. And also part of my thesis project is I actually simulate repeatedly lots of these systems, and they all have the same mass, but they have different age, different formation history, live in different neighborhoods, and you can see that some of them are more concentrated, like this right-hand side one, and basically have higher density contrast. And some of them just have more neighbors, like this one. And some of them are just boring and quiet, and like this one. And that's why because looking at these galaxies are basically what astronomers can do. And how do we, just by looking at them, infer their mass? And this simulation sample is going to help us understand the mass. So finally, I'd like to mention this dark energy survey project, which the cosmology group in the University of Michigan is highly involved. So this project is building this dark energy camera, which has been mounted on the Blanco telescope in Chile, and just see its first light in September. So in this project, we expect to observe more than 100,000 galaxy clusters. And we are going to measure their mass, and then we are going to infer the properties of dark energy, which will be exciting. And my simulation of those galaxy clusters is hopefully will help this mass calibration of these clusters. And to summarize, at the very beginning, I talked about this cosmic microwave background, which tells us about the initial condition of the universe. And then later on, I talk about how this small perturbation is amplified by gravity and how structures form and how we use computer simulations to simulate the formation of them. And finally, I talk about how dark energy causes the acceleration of the universe and slow down the formation rate, the growth rate of cosmic structures basically makes there fewer structures in the universe than we expected. So finally, I'd like to come to our balloon again. Now I'm going to do a more realistic demo. So I said that the universe, originally, the universe has been expanding. And because of the gravitational pull of dark matter, it's going to slow down. It's going to slow down because of the dark matter. But relatively recently, about 5 billion years ago, it's accelerating its expansion. And we don't know about our fate of the universe yet, but we do know about the fate of this guy. And we are going to, who doesn't want it to pop? We still have a chance. Oh. Thank you for your attention.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.